In this video, we're going to discuss the concept of a stack. A stack is an abstract data type. It's kind of like a spring-loaded stack of plates. So what are the associated behaviors? Can you access a random element randomly? No. Can you tell how many plates? No. What happens when a new plate is added? It goes on top. Can you tell when it's full? How? Can you tell when it's empty? Stacks are last in, first out, or LIFO objects. There are operations on a stack, including is it empty, is it full, remove a plate from the stack, add a plate to the stack. Operations on a stack are typically empty, full, pop, which returns the element from the top of the stack, push, which pushes a new item onto the stack, and init, which actually creates this, or sets the stack up. And this is in the ADT. So here's an example. Consider an arbitrary mathematical expression with the numbers 1, 2, 3, operators, etc. Write an algorithm that uses a stack to process an expression to ensure all parentheses, brackets, and brackets match. Input is the arithmetic expression. The output is yes or no on whether parentheses, brackets, and braces and brackets match. So here's some pseudocode for it. We initialize our stack. While input, if it's a bracket or curly, etc., we push it onto the stack. If it's the closing one, we pop it. If the item that we pop off matches the other side of the item we expect, we continue. Otherwise, no. At the end, if the stack is empty, we return yes, they match. Otherwise, no. So, A plus B, yes. This would be a no. Yeah, and so forth. So, a stack in STL is a specialized container, and it implements a LIFO, and it defines push and pop. But pop, like before, doesn't return the top element, it just pops it. And internally, it's implemented as a deck. So we've got push, inserts, top, returns the next available element. Pop removes it, size, and empty are also provided. Pop removes the element but doesn't return it. Top returns the element but doesn't remove it. Pop and top have undefined behavior if the stack is empty. So here's a very simple example. We push 1, 2, and 3 on the stack. We're going to print out the top, which would be 3, because remember it's a FIFO. We're going to pop it, and then we're going to print the next item, which would be 2, which is also a FIFO. We pop it. We're going to modify the remaining element and make it to 77 instead of 1. We're going to push 4 and 5, so 5 would now be on the top of the stack. We're going to pop the first one, and then we're going to go through and print the rest, which would be 4 and 77. So, classes that use an encapsulated object of a specific container class as its underlying container provide a specific set of member functions, and those are called container adapters. They're not first-class containers because they don't provide the actual data structure implementation in which the elements can be stored, and they don't support iterators. Stack enables insertions into and deletions at one end of a data structure. The underlying container shall support the following operations: empty, size, back, push back, and pop back. So it can be implemented with any of the sequence containers, list, vector, and deck. So we can tell it, the default is a deck. We can tell it we want to use a vector. And we can tell it we want to use a list. The elements, so each of these elements are implemented using these internal function calls. Push is a push back, pop is a pop back, top gets the back, etc., because we deal with the end of the stack. You have to use include stack, and here are the different prototypes. They return reference types when they return something. So we want to write a C++ program that initializes the content of a stack to a sequence of numbers and then pops the element one by one until it is empty and calculates the sum. So we're going to include our normal includes, including stack, Start our algorithm. Declare a stack of integers. Our sum is 0. Now go from 1 to 5 and push the values on the stack. So what the stack will look like after is 5, 4, 3, 2, 1. While the stack isn't empty, we're going to pop the value, add it, or we're going to grab the top value, add it, and pop it, and then output our sum. So here's another example. A guest indicates that he can't eat mushrooms and needs to have them removed. Write a function that accepts a reference to a stack and an integer target and returns true if target was removed and false otherwise. You can only use stack data structure in operations. The order of the remaining items should be the same as the initial stack. So here's how we do it. We have our stack and a target. So we have our function remove target, which takes a stack, and we're going to implement another temp stack. So we're going to go through, and while the stack isn't empty and it doesn't equal top, the top doesn't equal target, we're going to push it on to the other stack, on the temp stack. If S is not empty, we found the target. So if S is empty, we restore the stack, and then we return the found target. And then we can run through and print out the stack. Hence, no mushrooms. And here's a little bit cleaner implementation of remove target. We'll run through. So now, if we run through this example, x equals 3, y equals 5, we push 8, then we push 2, and then we push 10, and we get the top and output it, so say 10. Similarly, if we pop stuff again, and that's our introduction to stacks. Again, the homework assignment will explore how to implement your own.